Good morning, everyone. So, myself, Dr. Aslesha from the Department of Aeronautical Engineering. Today, we are in the course of high-speed aerodynamics. We are going to see the Hugoniot equation. So, the derivation part. Previously, we have seen that equations, everything, right? So, we will see the in detailed derivation of the Hugoniot equation, how it has been come. Okay. So, coming to the Hugoniot equation, so what we have, we will just recall the everything and we will just directly go for the derivation. So, the normal shock wave are coached in terms of velocities and Mach number. So, whatever the normal shock waves are, those are the in terms of velocity and Mach number we are coached, right? So, emphasize the fluid dynamic nature of the shocks. However, whatever the basic static pressure is there, it will be increasing across the shock wave. And the wave itself also can be visualized as a thermodynamic device which compresses the gas. So what we are telling is like, we know for the normal shock wave, whatever the flow properties are there ahead of the shock wave, that is ρ1, T1, P1 will be more than behind the shock wave. They are more than the ahead of the shock wave, right? P1 and T2 is greater than T1. So same one, the wave itself also, how we will be able to, we will be visualizing as a thermodynamic device which compresses gas. So in terms of thermodynamic device which compresses gas, we will be visualizing the wave like that, right? So indeed, whatever the changes will be there across the shock wave can be expressed in terms of purely thermodynamic variables without explicit reference to velocity and or Mach number. So generally, basically, whatever we have seen previously, all those expression of continuity equation or the pressure variation, temperature change, and the density change, all are in terms of the Mach number we have seen, right? So now what we are telling here, whatever the wave itself, we will be visualizing as a thermodynamic device which compresses the gas. So similar manner, we are going to see the thermodynamic variables also. The equations, the expressions will, whatever the changes will be there, they will be purely in terms of thermodynamic variables, not in terms of velocity and Mach number. So, same one, we know the continuity equation, ρ1 u1 equal to ρ2 u2. So, from there we are finding the u2 expression. Then we know the momentum equation, that is P1 plus rho u1 square equal to P2 plus ρ2 into u2 square. So, what we are doing here, in place of u2 square, we are going to substitute the continuity equation. From continuity equation, what we got the u2. So, we are going to substitute inside this expression. So, once this is done, we are going to calculate for the u1 square, right? So, what is the u1 square? So, u1 square equal to, so just solve it. Take it out, this particular one, this side means what it will be? P2 minus P1 plus you take out this particular expression to the other one, opposite direction. So, what it will be there here? ρ1 u1 square, ρ2 will be getting cancelled out, 1 ρ2 will be there down. So, it will be ρ1 square into u1 square. So, then you divide with the ρ2 minus u2. So, once you solve it, you will be having this particular expression, we will be getting it, right? So, what will it is nothing but, so ρ1 u1 square equal to P2 minus P1 plus ρ2 into ρ1 by ρ2 square into u1 square. So, this is square will be getting cancelled out. So, now what we are trying to find out, u1 square, right? So, let us take out this particular expression to the opposite direction. So, what it will be there? ρ1 u1 square minus ρ1, plus, minus ρ1 u1 square by ρ2 into u1 square equal to P2 minus P1. So, now if you are taking out the common of u1 square, so it will be ρ1 minus ρ1 square by ρ2 equal to P2 minus P1. So, from there what we can write? So, u1 square equal to P2 minus P1 divided by, so what we will be doing for this particular one? Do the LCM. So what it will be? Rho 2 minus rho 2 rho 1 minus rho 1 square into rho 2, right? So once you do the normal, okay, let's do like this, divided by rho 2. So what we can write? So this further can be writing as P2 minus P1 by, so we take out the rho 1 common, okay. So rho 2 minus rho 1 into rho 1. So this rho 2 will go above. So what we can write in expression? So U1 square equal to P2 minus P1 by rho 2 minus rho 1 into rho 2 by rho 1. So this is we will be getting. So similar manner, previously we have written U2, now we will be writing the U1. So from there U2 square will be is nothing but this particular expression. So what we know that the energy equation, H plus U square equal to constant. So if you are taking the two region means H1 plus U1 square by 2 equal to H2 plus U2 square by 2. So now from there what is enthalpy? We know equal to H equal to E plus PV. So V is nothing but 1 by rho, right? So we can write E plus P by rho we can write. So now what we are going to do? We are going to substitute H equal to E plus P1 here. So then it will become E1 plus P1 by rho 1 plus U1 square by 2 equal to E2 plus P2 by rho 2 plus U2 square by 2. So this is what the expression we will be getting. Now what we are doing, we got to know what is U1 square, what is U2 square, right? Now we have substituted this particular expression inside that one, right? So now we try to solve what is the value for E2 minus E1 we will be getting. So because we want to solve this particular expression and see how it will become. So now what we can write here, so from this expression we are writing E2 minus E1. Okay, so that is equal to first one P2. So we have taken this one in that side, right? So let's take out all these terms to the from right hand side to left hand side. We have taken the E1 to the right hand side. So let's take out this entire term to the left hand side. So when you take out two entire terms to left hand side, what it will be? P1 by rho 1 minus P2 by rho 2 plus half P2 minus P1 by rho 2 minus rho 1. So let's write like this, into rho 2 by rho 1 minus of half into again P2 minus P1 by rho 2 minus rho 1 into rho 1 by rho 2. So this is what we will be getting, right? So now from this one we try to solve the easiest one what we can be done for this. Okay. So now let us write first initially. We solve for this particular one. We take out minus of, then what it will be? P2 minus rho 1 P1 P1 rho 2 divided by rho 1 rho 2. So this is from the first section. So negative we take the common, so that we in terms of to make it solve for the mathematical expression, to make it easier for us, we are interchanging. So if you are making it minus means, so it will be minus of P2 rho 1 it will be. So minus into minus plus P1 rho 2 it will be there. So we don't have an issue. Now from this expression what we can take out the common, half into P2 minus P1 by rho 2 minus rho 1. We can take out the common, right? So what expression will be left out? So rho 2 minus rho 1, rho 2 divided by rho 1 minus of rho 1 divided by rho 2, right? So now what we can further we can write like, same, let's keep P2 rho 1 minus P1 rho 2 divided by rho 1 rho 2 plus half into P2 minus P1 divided by S2 minus S1. So now this one we can write rho 2 square minus rho 1 square by rho 1 rho 2, right? further what we can write. Now from this one what we can do? Let us take out the common of row 2, row 1 to this side. So now what it will be? Undo the LCM also. So if you do that one, row 1, 2 into row 1, row 2, we have taken out the common. So once we take out the common, what will be the above expression will be? Minus of P2 row 1 minus of P1 row 2. So that will be there as it is. Now what we can write? Row 2 minus row 1, row 2 square minus row 1 square as row 2 minus row 1 into row 2 plus row 1. So here 1 row 2 minus row 1 and row 2 down row 2 minus row 1 will be getting calculated. So above 1 we will be writing in terms of row 2 minus row 1 into row 2 plus row 1. So this one and this one will be getting cancelled out. So expression will be left out will be, so into 2 will be there, plus P2 minus P1 into what we have? Row 2 plus row 1. Right? So this is what the expression which we got. Now from here what we will be writing further? So 1 by 2 row 1 row 2 into minus 2 P2 row 1 plus 2 P1 row 2 plus P2 row 2 plus P2 row 1 plus minus P1 row 2 minus P1 row. So this will be there. So now from here what we can write? Minus of half row 1 row 2 into, so 2 P2 row 1 and we have 1 P2 row 1. So it will become P2 row 1. Then next one will be 2 P1 row 2. Here 1 P1 row 2. So this is also, sorry, this will be minus, right? So this will be P1 row 2 which will be there as it is. Then what we have? We have P2 row 2 plus, sorry, minus P1 row 1 will be there. So now from here what we can take out? P2 plus P1 into row 2 minus row 1. So if you do like that one, what it will be there? P2 minus row 2. So fine. These two we will be getting this. Then P2 minus P1. So from here we will be getting this. P1 row 2 we will be getting this. P1 row 1 minus row 1 we will be getting. So now from here we can take out the common like P2 plus P1 by 2 row 1 row 2 into row 2 minus row 1. We can write like this, right? So further this expression we can write what we got? E2 minus E1 equal to P2 plus P1 by 2 row 1 row 2 into, we got row 2 minus row 1, right? So row 2 minus row 1. So now if you take this particular term inside, we can write further P1 plus P2 by 2. So if you multiply it inside, what it will be there? Row 2 by row 1 row 2 minus row 1 by row 1 row 2. So row 2 will get cancelled out, row 1 will be getting cancelled out. So we will be left out with P1 plus P2 by 2 into 1 by row 1 minus 1 by row 2, that is equal to E2 minus E1. So this what we know, V equal to 1 by row, right? So V1 will be 1 by row 1, V2 will be 1 by row 2. So this is nothing but the Hugoniot equation which we got. So this is the derivation for the Hugoniot equation. So as you can see, all the terms are in terms of thermodynamic expressions only. We don't have the terms in terms of either in velocity or Mach number, right? So what we can see is like it is advantageous because it relates to the thermodynamic quantities across the shock wave only, and we are telling this particular expression of thermodynamic state variable, whatever is there, it is a function of two states variable, that E will be pressure and specific volume which will be there. So that P2 will be function of P1, V1 and V2. So we will be plotting the PV graph. So that is nothing but the Hugoniot curve which we will be telling. So this curve is nothing but the locus of all possible PV condition behind the shock waves of various strengths for one specific set of upstream values of P1 and V1. So by giving one set of P1 and V1 values, so how it is going to vary the P1 and V1 values behind the shock wave, right? So we will be giving one set, that is P1 and V1, and we will be seeing the expression of the P2 and V2, how it is going to vary. So this is nothing but, this curve is nothing but the Hugoniot curve. So that is shock wave expression, and this particular one is the isentropic curve where we will be taking PV power gamma equal to constant. Now what we know? We know the particular expression of P2 minus E1 equal to P1 plus P2 by 2 into P1 minus V2, right? So, but what we know further, E equal to CVT, this equation you know, and T equal to PVRT for we also knew, PV by R we also know this one. So now what we are trying to do is like we substitute this CV value inside this expression. Now let's see how it will be coming. So the expression will be CV T1 minus CV T2 equal to P1 plus P2 by 2 into V1 minus V2. Okay. So what is T1? PV by R. So now what we can write, and what is CV? CV is nothing but R by gamma minus 1, which we have seen in the high-speed aerodynamics initial classes. So let's substitute R by gamma minus 1 and T value inside this expression. So what it will be there? R by gamma minus 1 into, sorry, this is 2, this is 1. Okay. So T2 is nothing but PV by R. So that is P1 V1 by R minus R by gamma minus 1 into, sorry, here P2 V2, this is P1 V1. So because we are writing for E2, right? So when we write for the second region, all the terms has to come in terms of second region only while we are representing. So first region if we are representing, all terms should be in the first one. So P1 plus P2 by 2 into V1 minus V2. So now from here, what we will be doing? R will be getting cancelled out. So what we will be having? P2, V2. So 1 by gamma minus 1 if you take out common. P2 minus V2 into P1 minus V1. So that is equal to P1 plus P2 by 2 into V1 minus V2. Now further this expression which has to come down, right? So let's solve for the P2 by P1. So for solving for the P2 by P1, what we will be going to do is like, we will be dividing the entire expression in terms of the P1 and try to see how it will. So now what we can write here is that, let us take out this divide by 2 here. Okay, for our convenience, mathematical convenience, we are going to take out. So now if you divide the entire term with P1, so then what will be there? 2 by gamma minus 1 into P2 by P1 into V2 minus V1. So this expression will be 1 plus P2 by P1 into P1 minus V2. So this is the expression, right, which we will be getting. So now further this one, if we are going to, if we try to solve for this expression, now what it will be there, we try to get the P2 by P1 terms one side and let us take the other terms into the other direction. Now what we will be having from here is that, so V1 minus V2 into minus plus of P2 by P1 into V1 minus V2. So that is equal to This entire, let us leave like that. Now what we are going to take out is like P2 by P1 to this side. So when we write the F1, P2 by P1 into V2 into 2 by gamma minus 1 minus of 2 by gamma minus 1 into V1 minus of P2 by P1 into V1 minus V2 equal to P1 minus V2. Okay. So now what we will be doing is like we will be taking out the LCM part. So if we take out the, or else let us solve the little bit more. Further, P2 by P1, if you take out the common, what it will be there? 2 by gamma minus 1 into V2 minus of gamma minus 1, sorry, V1 plus V2. That is equal to V1 minus V2 plus 2 by gamma minus 1 into V1. Right. So now what we try to do is that we try to solve this expression. So now what it will be there? P2 by P1. So let us solve for the V2, right? V2, if we are taking out the common, what it will be? 2 plus gamma minus 1 by gamma minus 1 into minus V1. So this is one expression. So left hand side it will be V1 if you are taking common, gamma minus 1 plus 2 by gamma minus 1 into, sorry, gamma minus 1 minus V2. This will be the expression. Now what it will be there? We will be having 2 gamma plus 1 by gamma minus 1 minus of V1. Then what we will be having? Gamma plus 1 by gamma minus 1 into V1 into minus of V2 we will be having, right? So let us write P2 by P1 equal to, so gamma plus 1 by gamma minus 1 into V1 minus V2 divided by, so here also gamma plus 1 by gamma minus 1 into V2 minus V1. Right. So now what we are doing? We are dividing the above one bottom with the V2. So when you do that one, what will be the expression we will be having? Divide this by V2 and this one by V2. Right. So when you do that one, P2 minus, P2 divided by P1 equal to, so we are dividing entire expression with V2 and this entire expression with V2. So what it will be there? Gamma plus 1 by gamma minus 1 into V1 by V2. So here V2 by V2 will become 1 minus 1 divided by, here V2 by V2 will be 1. Then what will be down expression? Gamma plus 1 by gamma minus 1 minus of V1 by V2. So this is nothing but the, for the calorific perfect gas, what we will be having the expression of in terms of the pressure ratio, right? So this is the entire expression what we got for the Hugoniot equation, where in terms of all the entire expression in terms of the thermodynamic properties, quantities only, but we didn't get in terms of the Mach number or the velocity here. So whereas if you are seeing for the Hugoniot curve expression for isentropic, what for calorific perfect gas value if you are taking, we know the E value is CVT we know, and T equal to PV equal to RT we know. So from there what we are writing here, T equal to PV by R. So we are substituting those values inside the equation and we are trying to find out the what is P2 by P1, right? So this is entire the derivation for Hugoniot expression. How we got? From there we have drawn the curve for the Hugoniot curve. So that is like by keeping into this final expression how our values are, by giving the initial conditions of the P1 and V1, how the graph is going to change. So for giving the P1 and V1, so we have that this particular P2 and V2 values we have been obtained. So and as you can see for the isentropic curve, it is directly from here the change. What is that? and Hugoniot curve we have. So once you linearly join between 2 to 1, the expressions which are going to come is like this for the curves which we are going to for the P versus specific volume. V is nothing but here specific volume, right? So this is the expression for the curve for the isentropic compression. Then we for calorific perfect gas, we have seen E equal to CVT and substitute T equal to PVR IR. We have substituted and got the equation for P2 by P1. So this entire derivation which I have been explained here, you might not be able to find in the textbook, but this particular one, once you get after substituting, once you solve this equation entirely, how I have derived, so you will be getting this expression. Okay, you can solve it by your own, or else you can follow this particular lecture to find how did we achieve this particular expression of Hugoniot equation only in terms of thermodynamic properties. Then later on, what we have done, like for calorific perfect gas equation, we have seen same for this particular expression of P2 by P1 as well. So where you substitute inside the equation of your E values, then then T value substitute, and you are just solving the mathematical expression. That's it. So that we will be able to obtain this particular expression. Okay. So once you get this particular V1 by specific volume values, and for gas con, if you are taking the air, then we can write gamma as 1.4, and specific volume at region 1 and region 2, if you are able to, if you are knowing about them, means we will be able to find out what is the P2 by P1. Either vice versa, whatever the unknown values are there by given conditions, we will be able to substitute it. We will be obtaining the expression. So this particular entire equations you will be finding in the modern compressible flow with historical perspective view by J.D. Anderson. But the derivation part, if you want to understand in detail, means you follow this particular lecture, and you will be seeing for the Hugoniot equation how we achieved those expression. That is nothing but what we have got, E2 minus E1 equal to P1 plus P2 by 2 into 1 by rho 1 minus 1 by rho 2, right? And this one further we have written as P1 plus P2 by 2 into V1 minus V2. So this is E2 minus C1 Hugoniot equation. So then what we have seen, P2 by P1 expression we have find out, where we consider for the calorific perfect gas. So how we got? So gamma plus 1 by gamma minus 1 into V1 by V2 minus 1 divided by gamma plus 1 by gamma minus 1 into minus of V1 by V2, right? So this is what the expression we've got, right? So these two equations we have been found. You can see this entire derivation in this particular session. So you will be able to understand easily how we got the Hugoniot equation and the calorific perfect gas expression, how you will be able to achieve for the Hugoniot equation. You just have to substitute the E equal to CVT. Then CV is nothing but R by gamma minus 1. Then T equal to, PV equal to R3. So from there T equal to, PV equal to R. From the T equal to PV by R. So that's how we have achieved by substituting these equation inside for the region 1 and region 2, and we have obtained this particular expression, right? So this is all about the Hugoniot equation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.